start with a little bit more extended session on hydrogen peroxide decontamination. As you could hear from Manfred already before, we use H2O2 also for the E-beam. It's a general surface decontamination technique we use in basically all of our isolators that come from SCAN. It's our core technology. And I will talk really briefly about all the basics of this technology. So I will start by some introduction. Then I will go through current trends of the aseptic processing and what new requirements are coming up for us as a isolator manufacturer and what new requirements on our H2O2 decontamination technology we see. Then I will go briefly through what kind of innovation we do in order to meet those requirements and just some example about the value of competence that we as a SCAN carry and give to our customers. So let's jump directly in. Why hydrogen peroxide? So it's nothing new, right? We know hydrogen peroxide for centuries that it's killing, well, bacteria and for its biocidal effects. But actually it has some nice features. We could say it's kind of ideal biocide. It has broad and non-specific activity. It's pretty safe to use. It breaks to water and oxygen, nothing toxic. It's quite good compatible with materials. And also, we can use it for ambient temperatures, which is very helpful for all the temperature-labile products. It has been scientifically proved, and nowadays, the validation procedures are pretty well developed, and what is important, accepted by the regulators. Actually, SCAN has been at the very beginning of this technology in use for isolators. In 2000, there was published quite a groundbreaking paper at the time, which led to and been referenced in many of the guidelines that are used even nowadays, which arise from SCAN, called Development and Quantification of Hydrogen Peroxide Decontamination Cycles. Just briefly, and this is also kind of the outline of this paper, how was the cycle defined? So usually we say it has 4 main phases. I added also additional one, cleaning and preparation. H2O2 is really surface decontamination, so we must make sure that the isolator is clean before we actually start this decontamination. And then we go through some preconditioning phase. This is where the isolator is starting. Also, often the conditions, the starting conditions inside of the isolator are adjusted. Often we dehumidify, for example. We reduce the humidity before we start the cycle. Then we go through the conditioning, which is the phase when hydrogen peroxide is injected into the isolator at very fast speed to reach the desired inactivation effect. And then we continue with some phase we call decontamination, where the effect is kept relatively at the stable conditions. There are different validation procedures how to prove that this decontamination effect is stable. And then we go to the aeration phase, where we remove the hydrogen peroxide from the isolator to any target level that is necessary for our customer. However, H2O2 is not without any mistakes, and we must say it has some limitations, and everyone has to be very well aware of them. First of all, it's a very complex system. It's based on biphasic nature of hydrogen peroxide and water. So there is always some level of condensation, some level of liquid hydrogen peroxide, as well as vaporous hydrogen peroxide inside of a system. It's totally different compared to what Manfred said before. In the E-beam, we have parametric release. If we reach some given dose, we don't need any bioindicator. This is totally not true for H2O2. There is no real parameters given in the guidelines what concentrations of vapor we need. It's really, validation and qualification approach is really crucial. Second of all, it's only surface decontamination. I already said we need to make sure that the surfaces are clean. We cannot penetrate to anything. We are only killing on the surfaces. On the other hand, we can penetrate through some things. For example, we can penetrate through Tyvek wrappings of the pre-filled syringes through different materials. And the residuals of hydrogen peroxide can make some bad effects on our future product filled in those syringes, for example. Despite these three basic limitations, it's still the method of choice for most of the isolators that are being produced as a surface decontamination technique. So I would go through the second part, which is what kind of trends do we see recently. Very generally, products have to be processed aseptically. There are many more products coming that cannot be sterilized, terminally sterilized. Of course, as soon as we can terminally sterilize, we go for it. But if we cannot, then it's very important to keep the process aseptic. We are seeing many more personalized products, which means we are doing more smaller batches. Extensive sterility testing becomes more expensive. This is kind of negative, for example, for the E-beam, which is really great for large scale, but for the small scale, it's probably too expensive. And important, really important lately is the products are more and more sensitive to the residuals of hydrogen peroxide, in other ways, oxidative stress. And this is what we really have to take care in many of our recent applications. Pharma industry is focusing to be more proactive and minimize the risk, obviously. If we imagine some sort of factory where our pharmaceutical production manufacturer, he has a bad luck, he has to do complete process aseptically. I will not go to the really reasons why, but let's say this is the way. There is the major quality target for the whole process to make sure that we reach sterility assurance level of 10 to minus 6. Now, what we have to take care, there can be anywhere within this process we can reach a problem, and as soon as this problem happens, we will have problem here. There is no step how to stop it, no filter, no sterility filtration, nothing like this. Anywhere, problem can happen. What the customers do, they try to build isolators. We usually start with aseptic filling, the major core of our company, right? So great, we have perfect isolator, we minimize risks there, but still there might be problems somewhere else. Second thing important is to have really, we must be sure that our sterility testing is correct. We don't want to have any false positives during our sterility testing. That's why we generate and manufacture and sell a lot of isolators for sterility testing. That's our second biggest market for scan. But we do also new things that are not so standard, like as isolators for bulk processing. We also make isolators for formulation and aseptic formulation. And what we are really recently focusing on is delivering new transfer systems. We can talk about material airlocks. We can talk about really material isolators. We can talk about mobile isolator transfer systems. All those things are really current and really demanded by our customers. Next thing is talking about being proactive to make sure that there is reduced risk for our product. We start controlling more the rooms. In the beginning of isolators, we thought maybe isolator, we put it into degrade zone, we're fine. This is not the case anymore at all. So there is demand also for room decontamination systems in the pharmaceutical plants. And we design big airlocks, or even really the whole labs are being regularly decontaminated with hydrogen peroxide. Also, expectations of regulators are a little bit shifting. What is absolutely required always is empirical approach. We cannot at the moment really predict how the hydrogen peroxide is working. We always have to provide really hard data. Use of BI as a process measurement tool is really important. We have to put the BIs in the isolator. We have to show that the BIs are being killed. But at the same time, we should not look at them as a target of the process. We should use them as a tool. So having one positive BI, that's not a problem. That's actually a good thing. We have to show where are the boundaries of the system. For this, there is really a good trend. Some of our customers, they are publishing maybe internal white papers or even really scientific community white papers where they say how to handle those positive BIs, because they will always happen. There can be cases where the positive BI will appear. And it's really good to have some sort of standards how to handle this. Increasingly important is to evaluate the hydrogen peroxide residuals and really to check also what is the effect on your product. This is one of the really increasing area also what the customers want from us. And last but not least, also quite relevant with new Annex 1 draft, make sure that the isolator surfaces are clean, maybe even validate the cleaning. That's kind of the major trends of the regulations which we see currently coming to the field of H2O decontamination. If I conclude, we're having trend of reducing the cycle times from hours down to minutes. There is trend to reduce the residual concentration of H2O from ppm down to really ppb, tens of ppb. There is a big trend on flexibility. We don't sell only integrated fixed decontamination systems. We sell mobile, also only integrated in the rooms. Anything customers are asking for. Important for them is scalability. Often we don't know how the product will be accepted. Maybe they want to extend the production soon. So also scalability of the isolator systems with integrated H2O decontamination is a big topic right now. And also, especially with the room decontamination, the decontamination must be robust over large conditioned space in the room. We cannot control the rooms so precisely as the isolators, talking mainly about temperature and humidity. Last but not least, evaluate your process boundaries. This is something that is becoming also increasingly important for the regulators to know where the isolator or where the process reaches this positive boundary, where the BIs suddenly start to be positive and start to grow. This is where you know, from here I have my safety margin in my process. How do we do all this? How do we reach all those expectations? If we look back on the conventional cycle, so we have those 5 main phases. And you can see in the phase 2 conditioning, we are putting in a lot of hydrogen peroxide in the system to reach this inactivation of the microorganisms. And then during decontamination, we just kind of continue adding some hydrogen peroxide in order to keep the decontamination running as we expect. And then we go towards the aeration. The aeration is the longest phase, so this is where most of the innovation starts, to reduce this aeration. How do we do this? There has been a lot of development among us and also other competitors of us to develop new catalysts. We also continued on this. Hydrogen peroxide decomposes on its own into water and oxygen, mostly on the surfaces of the isolator. It will on its own decompose to water and oxygen. But if you help a little bit by some catalysts, you can make this decomposition extremely fast. We developed our Scan Nanox catalyst, which is based on the nanotechnology. We're using ionic silver that is then put on the carriers of alumina, silica. And with this, we reach a catalyst that is much more efficient than any standard catalyst. We have much more surface area. We have smaller pressure drop in our systems. If we integrate such catalysts into the isolators, we accelerate the hydrogen peroxide decomposition so that in single pass, we reach 0.1 ppm. This is crucial because then we can supply all back from the isolator directly to the pharmaceutical room. We don't have any pressure balance issues, and we can increase the air change rates as much as possible so that we actually even can build a once-through aeration concept systems. This works incredibly, and we can really maximize the aeration speeds with this solution. Further on, we focus on optimization of the aeration pattern. So we are really using the CFD not only to show off in some slides and presentations, but to start thinking more how to really optimize the flow, what design of our isolators is optimal for best aeration. When we optimize isolators like this, we reduce the aeration phase significantly. However, for many applications, mainly talking about material airlocks, still not enough. Still, too much hydrogen peroxide would be needed in the system. And for this, we had to focus on the conditioning and decontamination phase. If I just go briefly through the basics of the technology, we have hydrogen peroxide, which is introduced on the hot plate. There it's flash vaporized. This is a process where we break this standard equilibrium of hydrogen peroxide and water, where hydrogen peroxide normally boils at higher temperatures, so it wants to condense first, but by flash vaporization, everything is vaporized at one point, and we create very saturated vapors which tend to condense. We guide them through the HEPA filter. Some, maybe quite a lot of this hydrogen peroxide condenses in the HEPA filter, but uniform hydrogen peroxide vapor gets through the isolator and here makes the needed decontamination. This is then often recirculated to make sure that all the decontamination is homogeneous and everywhere reached. However, mainly the HEPA filter here is the issue. We have a lot of condensation in the HEPA filter, and this makes the cycle time longer in the end. What is the first possible innovation? We can directly inject the vapor inside of the system. We skip the HEPA filter. We actually still have the HEPA filter for standard operation of the isolator, like production, but for the decontamination itself, we close the isolator and we directly inject the hydrogen peroxide into the system. This makes it much more effective directly. We inject very high concentration of hydrogen peroxide inside, and this tends to really condensate everywhere. The problem here is maybe the concentration of injected hydrogen peroxide is so big, we might have overcondensation at some parts of the system, while the others will still not need quite a lot of time to reach desired decontamination. This can be a problem, especially for those very sensitive products where you really want to make sure that the residual content of the hydrogen peroxide is minimal. And this is what leads us to direct micronebulization. Here we don't break this primary equilibrium of hydrogen peroxide and water. We just bring the hydrogen peroxide in the system, but we generate a big surface area, which we use as some sort of vaporization. And also, directly by injection, we mix the chamber with the compressed air. So very fast, we distribute the hydrogen peroxide over the entire chamber. Then we have a system where little particles of H2O2 are flying around, and they are vaporizing and saturating the environment around them. This environment, which is then saturated vapor of H2O2 and water, is then condensing on the surfaces. And this is how we reach homogeneous kill all around the chamber. We distribute the droplets very fast by direct injections. We generate very large liquid vapor surface to achieve the saturation of the system very fast. And for the first particles that are directly injected in the system, we actually also reach this effect of flash vaporization because the particles vaporize fully. So it's the same as we are vaporizing them on the hot plate, but actually with much less energy needed, we don't have to preheat the hot plate, etc. This leads us to very rapid and reliable surface decontamination effect, which we use in our latest, fastest material airlocks that we produce. If we look at the system, still preparation, preconditioning, system startup, probably still needed, but then the effect is reached with much less of hydrogen peroxide use. Actually, we use one third or even less of hydrogen peroxide than we normally use for our standard decontamination system. And we don't need to inject more of the H2O2 during the secondary phase of killing, which we now call dwelling. Actually, this phase is not often even needed. Often we reach the desired kill already during the conditioning phase. But for some systems, especially if we have bigger rooms, then some dwelling phase is necessary because it needs some time to really be sure that the kill is everywhere reached. But we don't need to inject more because the particles, the droplets of hydrogen peroxide are still flying around and still keeping the saturated concentration that we need. Aeration is then very fast because we didn't inject so much hydrogen peroxide in the system. This is the basic of our micronebulization. We are able to go with cycle times down to minutes, and we still reach the desired 6 log total kill, or in other words, more than 10 log spore reduction. If I go briefly about the qualities, we are fast and robust process. It's efficient, less H2O2 is consumed. Flexible, can be integrated, fixed or mobile, still validated with biological indicators or by chemical indicators additionally. And total kill is reached with good material compatibility. We are really excited about this technology because it seems it's what is now required by the market. Very flexible, that's the main reason why this is so exciting. I would like to go just shortly about the last thing, which is the value of competence. It's not only about the technology, it's not only about having the shortest cycle, it's about how the cycle is developed, how we can really sell it to the customer and to the regulatories in order to get our product registered. I would like to talk shortly about some case study with one big pharma partner of us. We are cooperating for very long. It's actually the world's largest producer of vaccines. And the target was develop a new process for room decontamination. They decided to be proactive and to reduce the risk in their laboratories, and they needed a new process which we never done before to decontaminate the room. We always focused on the isolators until then, and suddenly a big new field for us. We cooperated with them, and in the end, this is also published in the PDA journal. We cooperated on the really quality by design approach basis. So we evaluated all possible parameters. We went through risk assessments, what could be happening, and we designed several designs of experiments which were done in the real life systems, real laboratories, to actually find out what are the ruling parameters of such a process. We ended up with a relatively simple plot, which is quite easy to understand. We have 3 major parameters of our process. Here you can see the D value. This would be in seconds. So this kind of shows the effect of those parameters on the cycle efficacy. We can show that with increasing temperature, the D values are getting shorter, meaning the cycle is getting more effective. On the other hand, with higher humidity, we are getting less effective. And with higher concentration of H2O2, we are getting more effective again. It all kind of follows the general thinking, right? With higher temperatures, all those droplets of hydrogen peroxide can vaporize faster. On the other hand, with higher humidity, actually the saturation is rather water than hydrogen peroxide. So it kind of makes sense, but with such a study, you can directly show to everyone how my process behaves. And this was really a big benefit for our customer. The study was very positively accepted also within the organization, but also by the regulators. And the boundaries of the process were clearly understood, very well accepted, and this made it very smooth to implement such a process. At the moment, this decontamination process is successfully applied worldwide in 400 rooms in very different geometries, but these geometries were covered within this study, so everybody knows, okay, within such rooms, this process works. this is what we give to our customers and what is really crucial for SCAN as an organization. Not only bring the technology, but bring the whole knowledge about the competence. That's what we do. Something is not really working here. I will just go. Hydrogen peroxide as such has many applications. It's not only pharmaceutical industry, but it's also healthcare market. We have customers from animal environments and also infection and disease prevention. But our focus is still on the pharmaceutical industry, but we see that the expectations are growing. Everybody wants to be proactive to reduce all the risks. And we see that this technology will have to be more and more flexible. So we're still developing new solutions and improvements. This really stopped working, so I will try to go further on. I would like to end with a kind of thought how to further innovate hydrogen peroxide. It has been so long time around. So we are looking at the specific needs of every customer, and we really communicate on the ground basis what is necessary. And then we focus on the empirical data. We run all different laboratories which bring us the necessary information, from microbiology, where we really test all different organisms necessary, through process development workshops, through chemical and analytical labs. And this all must be used smart. So we use advanced techniques of statistics. We use only design of experiments for our core studies. And we also validate our CFD models. So we don't just show off, but we really work with real data to make sure we say correct things. This is the last slide of me. We believe that it must be a complete package delivered. Not only the technology on the paper, but it has to be reliable, it has to be flexible. We have to provide all the know-how and service to the customers with given quality. This is our core competence of SCAN, and this is how we see hydrogen peroxide. We have some publications on our web pages. If you are interested, you can search or just ask us in the booth afterwards. Thank you very much for your attention. I'm looking forward for questions, if there are any. Yeah?
You talked about the effect of humidity and D-value. So if you're decontaminating a room, would you expect, thank you very much. Would you expect your clients to have developed clean rooms with humidity control in all cases? Because that's not always the case and not always that convenient.
Exactly, yeah. So I have actually my microphone with me. Sure, this is exactly the feeling. That's why we have to make sure that the cycle for room decontamination is robust enough within acceptable humidity range. Of course, it also means that we have to look at the validation a bit more customer specific. Some customer will have big range of humidity, some customer will have small range of humidity.
So it will change over the course of the year. In the winter, it will be drier, the lower RH.
Exactly. This is another issue because we know that humidity is a crucial parameter. It's relatively easy to work inside of the isolator where you can dehumidify to some given range to allow some process variation, but not too much. In rooms, this is really an issue. And also the issue is one cannot control it when the validation is performed. That's why we're doing a lot of studies inside. We do really many case studies with our customers to cover all these ranges of the conditions and to make sure that the process is robust within the whole range of humidities, not only humidities.
Can I just ask what you're talking about the catalyst.
Sorry.
What was the starting concentration to get down to the less than 1 ppm or 0.1 ppm?
It depends what kind of process we are we are running, but usually we're talking about something 600 ppm, or it's mostly less than 1000 ppm.
Any other questions? No? Okay, thank you, Martin.